Hey guys, and welcome to another edition of Physical Science Online. Today we're going to be talking about the scientific method and also the metric system. So let's dive into the scientific method to start. So here's the deal. The scientific method is something that we've come up with as scientists and been like, this is the best way to get information that we know won't change once we figure out what it is. So for the most part, there's a process here, right? The first thing you need to do is observe the natural world, kind of what's going on. The next thing you need to do is you need to experiment, which is kind of a more specific observation. And then once you have your experiment, once you've done it, then you can start to make conclusions about the data you've got. That's pretty much the scientific method in a nutshell. Here's how I like to visualize the scientific method, is that it starts with observation. We move on to experimentation. And in observation, there's kind of two steps. First step is we have to come up with what's our purpose? What are we trying to observe? And then the next thing is we need to make kind of a statement or a hypothesis, which we talked about earlier. Experimentation, we've got the experiment, we collect the data, and then we do the reasoning where we analyze the data and we conclude, we make statements. Now, what you'll notice here is that this forms a nice little triangle here, or kind of a more cyclical pattern. The idea being is that once we have a conclusion, once we've come up with some ideas as to what we think the data shows us, we can then go back and say, okay, well, we made this conclusion. What new observations can we make about this conclusion? And that's how we learn more, or that's how we figure out if our hypothesis was wrong. What can we do to change it so that we can make a hypothesis that is correct? Type deal. So we're going to show you a couple other hypotheses, and my hope is to kind of refer back to the scientific method as we talk about that. But just know that the scientific method isn't just something that like one person came up with and we all decided to stick to. It's definitely something that over time people have come up with different scientific methods. And as of 2020, this is kind of the best way to do things so that the results we get don't change over time. That's not to say that there aren't experiments that do change over time, but usually that's because something was wrong in their experiment or we learned new information. Either way. Okay, observation stage. Here we go. The observation stage, we've got the purpose, and that's the reason why the experiment is done. I put in parentheses here, that's the why. And then we have the hypothesis. You should already have a definition for a hypothesis, but just so you know, it is an educated guess about something that's happening, whether that's a physical event or a phenomenon. The most important thing about a hypothesis is that it follows an if-then format. If it doesn't follow an if-then format, it's probably just a purpose. So if you're wondering, for example, why is the sun so hot? That is not a hypothesis. That is a purpose statement. So an if-then statement about why is the sun so hot would be something along the lines of, if nuclear reactions happen in the center of the sun, then heat will be generated, or something like that. And that would be an idea that we would have to explore. We would have to look at maybe the nuclear reactions happening in the sun and figure out how much heat they generate, and then kind of make some observations from that. Okay, so I just did one about the sun. Here's your opportunity to create two hypotheses of your own given these purposes. First one is, how does gravity act on cats? And the second one is, are melons sledgehammer resistant? So you want to take these two purpose statements and create an if-then format. Remember, your if should have your independent variable, the variable that you are not changing, and the then should have the dependent variable, the variable that you are looking to change. So kind of think, what kind of if-then statement could I make? And then make sure, oh, do I have an independent and a dependent variable here? Okay, cool. For the gravity acting on cats, I said if you drop a cat, then it will fall until it reaches the ground. That was my if-then statement. So in this case, we would be measuring number of cats dropped. That would be our independent variable. And then the dependent variable would be how far they fell after they reached the ground. So that would be kind of what we're measuring. And hopefully the idea would be that it would move like 0 feet after it hit the ground, right? Are melons sledgehammer resistant? If you hit a watermelon with a sledgehammer, it will break. So maybe here your independent variable would be number of watermelons hit, and then you'd look at how much they broke or how many of them did break. So maybe you might have hit 100 watermelons and 99 of them broke, but one watermelon was a really tough one and was able to stay together. That could be your data, for example, in that experiment. Hopefully at this point in time, we're feeling comfortable with hypotheses, and we're seeing that even if you do have some a little bit crazier of hypotheses, you can still make if-then statements that have your independent and dependent variable. Okay, let's move on to the experimentation stage. This is where we actually, do the thing. We actually figure out the data. So, an experiment is a scientific procedure used to test a hypothesis. Data is just the facts that we collect, and we can reference them later. We can analyze them. So that's what an experiment and a data is. You'll be doing an airplane lab. So think about it. What kind of data are you collecting about the airplane lab? Do you guys remember the airplane lab from earlier? Remember, you're taking an airplane, same design, different weight, and you're seeing how far it travels. So think, what kind of data are you collecting for the airplane lab? To answer your question, what data are you collecting for the airplane lab? You would be collecting data on distance traveled, right? And also, you'd probably be collecting data on the type of airplane. You'd probably want to record what your airplane looks like as well. That would be your independent variable, and then your dependent would be distance flown, for example. Okay, reasoning. Now, this is where we do the analysis and the conclusion. For analysis, we just interpret data. And for the conclusion, that's going to be a summary of the lab and a summary of all of its results. So conclusion is kind of where things get tricky. There's a lot of times that you can collect data and then you can conclude something that maybe reflects some of the data, but not all of the data. So most of the time, if you see a study that makes a conclusion that's later proven to be false, like for example, there was a conclusion done by a study about vaccines that vaccines caused autism. That's been disproved many times by future studies, but what tended to go wrong was the fact that, number one, the data wasn't great just because they didn't have enough control variables, or some of the variables they thought they controlled were not actually controlled. And then number two, they made incorrect conclusions off of their data because they didn't recognize that there were some other variables at play that weren't being controlled properly. So that would be an example of how bad conclusions can come from good data. So here's a question. How will you know which one of your airplanes is the best? Think about this. If you're throwing an airplane, is it possible that maybe one airplane just flies better due to the style in which you're throwing? How big of an issue is design versus style of throwing? So think, are we keeping our throws consistent? How much of it could be due to luck? Maybe if we took more trials, we might see that other airplanes succeed and other airplanes fail. How much of it could be due to the durability of the airplane? If you throw it once, maybe the point gets all bent and then it doesn't throw as well the next couple of times. These are all things to think about as other things that could be playing in the airplane lab, other things that could be at play in the airplane lab. Cool. So now I want to talk a little bit more about the scientific method, which is going to answer this question, how do we record data? So what I want you to do is answer these questions to the best of your ability. You might not know exactly how much a black bear weighs, but give it an estimate. What are your thoughts? Great. Okay, so how long is a football field? Football field is 120 yards. 100 yards are marked out, and then the end zones are 10 yards each. So that adds up to 120. Hopefully you said 120, not just 100. How much does a black bear weigh? They weigh about 400 pounds. And how large is a milk jug? A milk jug is usually either a half gallon or a full gallon. So in this case, here's a full gallon of a milk jug. Now, in the world of science, we would not use terms like yards, pounds, or gallons. Instead, we would use terms like meters, kilograms, and liters. Meters, kilograms, and liters are a part of what we call the SI system. SI stands for Système International. It's French. Sometimes we also just call it the metric system. So we're going to talk about the SI base units. These are all metric system units. You're going to want to write this down somewhere in your notes. For length, the unit that we use, this would also apply for width and height. Anytime we're measuring distance, we use meters. For mass, we use grams. For volume, we use liters. For time, we use seconds. And for temperature, we're going to use degrees Celsius. So what I would like you to do for each one of these guys is record the unit that you would use: meters, grams, liters, second, Celsius. So how do we use the metric or the SI system? Everything in the metric system is going to have a prefix and it's going to have a suffix. The prefix is going to tell you the size of the measurement. So you might see something like kilo, which is a big size, or you might see something like milli, which is a small size. So maybe you've heard of kilometers, but then you've probably also heard of things like centimeters or millimeters. Kilometers or kilometers is a really, really large distance. It's close to a mile. Centimeters is a really, really small distance. There's about 2 to 3 centimeters in an inch. And then the suffix is going to be the type of measurement. So you could have kilometers, kilometers, which is a measurement of distance, or you could have kilograms, which is a measurement of mass, not weight. It's a measurement of mass. So there, for the example, I wrote down milliliters, which is a very small measurement of volume, liters. And then for the abbreviation, every unit in the metric system has an abbreviation. You kind of take the first letter of the prefix and the first letter of the suffix. So milliliters would be abbreviated M and capital L. Here's some more information about how big a milli is. We'll get into that in more detail in a bit. Liter is the base unit for volume. And then I said that abbreviation uses the first letter of the prefix and the suffix. So I would definitely write this down. Know that the metric system is made up of a prefix and a suffix. That's where you get it. Prefix tells you the size, suffix tells you the type, and then the abbreviation is the first letter of each. Here is the metric system all lined up. So there are 7 different prefixes that will have you know. I guess there's technically only 6, because right in the middle here we have base. Base is just no prefix, so that's kind of the middle. And then deci, centi, and milli, those are all smaller measurements. So deci is 10 times smaller, centi is 100 times smaller, and milli is 1,000 times smaller. Deca, hecta, and kilo are all bigger than the base unit. So let's say, for example, meters. Decameters is 10 meters, hectameters is 100 meters, and kilometers or kilometers is 1,000 meters. So you can remember these different scientific measurements with the abbreviation King Henry died by drinking chocolate milk. So that's a little acronym we have for you. And then here I've kind of posted how big each one is compared to the base unit. So centi, there are 100 centimeters in 1 meter versus kilo, there's 1,000 meters in 1 kilometer. That's kind of the ratio for each one. So deci, centi, and milli are fractions of a base. Deca, hecta, and kilo are 10, 100, or 1,000 times the size of the base. So the nice thing here is that everything is on a 10 size scale. So another way of thinking about this is they're all 1 decimal point away from each other. So for example, if you wanted to convert kilo into meters, you would just move the decimal place over to the left 3 times. If you're in millimeters and you wanted to convert into liters, you would just move the decimal over the other way 3 times. And we'll talk about how to do that coming up next. So let's say you have 3.75 meters. You might be wondering, how many kilometers is that? Well, we know that to get from meters, our base, to kilometers, we're going to have to move over 3 times. 1, 2, 3. So if we take our number 3.75 and we move it 1, 2, 3 times over, that will turn into the number 0.00375 kilometers, which makes sense. 3 meters is like a really, really small amount of almost a mile, right? So we would think that it would be a really small fraction of a kilometer. The next question is, how many millimeters is 3.75 meters? So let's look at part B here. Now we're going the opposite way. So our number is going to start at 3.75. We're going to move the decimal 3 times, and it's going to become 3 times as big. So 3,750 millimeters is the same thing as 3.75 meters. So that's using the metric system to convert from one type of metric unit to another type of metric unit. Really all you're doing here is you're using this abbreviation, King Henry died by drinking chocolate milk, or kilo, hecta, deca, base, deci, centi, milli, and you're just moving the decimal point. So you want to know this KHDBDCM. You want to know this abbreviation, because if you write it out like that, you can then move the decimal point on these guys first and then move it on the actual number second, and that'll save you a little bit of time. And hopefully that'll make it really, really easy. So here's what's going to come up. Eventually, we're going to have a quiz on this. The quiz will be called Quiz 1.2. You'll be asked to talk about, I'll give you a measurement. Maybe I'll say like, how hot is the sun? And you'll have to be like, oh, that is a temperature measurement. And then also feel comfortable converting from one type of metric unit to another type of metric unit. So you're changing the prefixes here. So converting from kilometers to centimeters, you should be able to do that. So come with questions when I see you in class. Hopefully you learned a lot today. That's my hope. And hopefully you also have a great day. Thanks so much for stopping in. See you next time.